Now we'll look at a very important example called counting partitions. And this example is important because it's a tree recursive process that's actually quite hard to write without tree recursion. So, one of the reasons we learn about recursion in this course is to solve problems like this one, like counting the partitions of an integer. What is that? Well, the number of partitions of a positive integer n, using parts up to size m, is the number of different ways in which n can be expressed as the sum of parts up to m in increasing order. Let me show you an example. Say we want to count the partitions of n equals 6 using parts up to size m equals 4. Here are all of those partitions, and this is an exhaustive list of everything that counts as a partition of 6 using parts up to size 4. So each line is a sum of different parts where the parts are in increasing order. So we have 2 plus 4, but we don't have 4 plus 2 because that's decreasing order. Okay, now notice that each part is always up to 4, but never bigger. So we don't include 1 plus 5. That doesn't count as a partition of 6 using parts up to size 4. But we do include 2 plus 4 and 1 plus 1 plus 4 as different ways of partitioning up the number 6. The idea here is we're counting the number of different ways that we can break 6 into groups. Now we can illustrate these different partitions by showing what we're grouping. So we have 2 here and 4 here, or we have 1 and 4 here, and all of the other options can be illustrated on a line as well. And the purpose of the count partitions function is just to tell us how many different partitions there are, not necessarily to tell us what they are. So in this case, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 different options. So count partition 6, 4 should return the number 9. Okay, let's understand how we would compute this value 9. And we need a strategy that will compute partitions for any n and any m that we pass in. So let me tell you the strategy first, and we'll work on the implementation afterwards. We're going to look for a recursive decomposition of the problem, meaning that we need to express this problem in terms of simpler instances of the same kind of problem. And we're going to do that by exploring 2 different possibilities. One is that we'll include at least one group of 4, or 1, 4, in the sum of parts that we use in the partition. And the other option, which is everything that doesn't include a 4, says that we're never going to include a 4 in the partition. We're only going to use parts up to size 3 or less. Now, splitting these 2 possibilities actually splits the set of all things that we want to count into 2 disjoint subsets, the ones that include a group of 4 and the ones that don't. Another observation is that everything that includes a group of 4 really just has to partition what's left over after we subtract 4. So in both of these cases, we're actually just partitioning the number 2. We can get it by just the number 2 or by 1 plus 1, using groups up to size 4 still. And what about the bottom half? Well, the bottom half is all the ways of partitioning 6, but using parts up to size only 3. So we're really solving 2 simpler instances of the same problem, meaning we'll make 2 recursive calls to count partitions. When we're trying to compute count partition 6, 4, using at least one 4 means that we then have to count the partitions of 2, again using parts up to size 4. So there's the simpler instance of the problem that we solve above this line. assuming that we use at least one 4. The other simpler instance is that we count the partitions of the whole number 6 using parts that are one smaller than the one we had before. So we're assuming we're not going to use any 4s, so we'll use parts up to size 3, and we need to count up all of those. So if we count up these 2 and we count up these 7, we'll get the 9 in total that we want in order to solve the problem. And that's the recursive decomposition that we'll use in order to count the partitions of a positive integer n. So tree recursion can be thought of as a technique for exploring different choices or different possibilities. These are the 2 possibilities we explore in this case. And what do we do with the result? Well, we sum the results together because we actually want all the different alternatives. And these 2 possibilities split that set evenly right here. Now, when we make one of these recursive calls, that's going to involve further decomposition in the same way. To count partitions of 6 using parts up to size 3, we'll divide that set of 7 up into 2 groups, those that use a 3 and those that don't. And here we have to count partitions of the 3 that remain. Here we have to count partitions of all 6 using parts up to size only 2. And each of those has recursive decompositions as well, sometimes here and sometimes here. And in this way, we explore all the different possibilities and can compute the final result that we want. Hooray! So we're finally ready to write some code. Once we have a recursive plan in place, we just need to write an implementation that executes that plan. So we define count partitions of a number n using parts up to size m. And let's start with the recursive case, because that's what we've been talking about. We count the partitions of n minus m using parts up to size m, which is all the cases in which we use at least one part of size m. We also count the partitions of n using parts that are smaller than m, or m minus 1. And then we sum together the cases in which we used an m and the cases in which we didn't. And that should give us all the different cases that we're interested in and the total ways of partitioning n. So for the case of 6, 4 as our inputs, this with m is count partitions 2, 4. And without m is count partitions 6, 3. Now we just need base cases. If we're partitioning 0, well, let's just say there's one way to do that, which is to add nothing together. If we're partitioning non-positive number, we've done something wrong along the way. There's no way to do that. And so we return 0, because we're not allowed to use negative parts. And if the maximum part size, m, gets to be 0 or less, well, there's no way to build anything out of parts of size 0. So we return 0 there as well. And that's our complete implementation of count partitions. Let's watch it work. So I'm going to define count partitions. I'll count partitions of a slightly simpler instance than we talked about before. We're going to count partitions of 5 using parts up to size 3. And here are all the different alternatives that we want to sum up. 1, 1, 1, 1, 1, or 1, 1, 1, 2, or 1, 2, 2, or 1, 1, 3, or 2, 3. So the original call to count partitions with n of 5 and m is 3 involves 2 recursive calls, one of which is partitioning the number 2 using parts up to size 3, which, if we do some computation, eventually returns the number 2. So if we try to use an m, like if we try to use a part of size 3 in order to partition 2, that's impossible. So that's why we get a 0 there. If we try to partition the number 2 with things smaller than 3, then we find there are 2 different ways, 1 plus 1 and just the number 2 alone. So those are the 2 different alternatives, and we've computed what we get when we count the partitions of 2. Now what happens when we count the partitions of 5 using parts of size 2 or smaller? Well, those are these 3 alternatives that we have left over. So if we run through the computation, we see many recursive calls, and after some amount of work, we compute that using m, which is the number of 2, we find 2 different ways of summing up the number 5. So here are the 2 different options that involve using the number 2, with parts size 2 or less. And the only thing we haven't accounted for is the sum of all 1s. So without m should include the sum of all 1s. We run some computation, try some different alternatives, and right here, we found that without using m, so using only 5, so computing 5 with only parts 1, there's a way to do that. We return that one way. So we return it here. We sum 2 and 1 together. We find out that without m we get 3. We sum 2 and 3 together, and we get the actual value we want, which is all 5 ways of counting partitions of 5 using parts up to size 3.